In 1943, a 55-year-old aircraft designer sat in his garden and threw marbles into a tub of water. He was trying to work out how to destroy the Ruhr Valley dams, the industrial heart of Nazi Germany. The RAF said it couldn't be done. The Air Ministry said it couldn't be done. Wallis did it anyway. The garden belonged to White Hill House in Effingham, Surrey, where Wallis lived with his wife Molly and their children. And the marbles weren't toys, they were data. He'd been at this since early 1942, flicking a marble across a washtub at a shallow angle, watching whether it skipped, counting the bounces, varying speed and spin, filming the results, scribbling notes. The Imperial War Museums have confirmed these experiments as fact, not legend. One of the most distinguished aircraft engineers in Britain was crouched beside a tub of water in his back garden, reinventing weapons physics from first principles. Because nobody else would.
To understand why, you need to understand what sat in the wooded valleys of northwestern Germany, and why it mattered more than almost any other target in Europe. 3 dams, the Möhne, the Eder and the Sorpe, impounded hundreds of millions of tons of water that fed the Ruhr Valley's industrial machine. Hydroelectric generators, canal systems, blast furnaces, coal mines, drinking water for the millions of workers who forged the steel and assembled the munitions that kept the Wehrmacht fighting. British strategic planners had understood this since at least 1937, when the Air Ministry first flagged the Ruhr dams as high-value targets. Knock them out, and you didn't just flood a few fields. You paralysed a war economy at its source. Simple to say, apparently impossible to do. The Möhne Dam alone stretched over 2,100 feet across its valley. A wall of masonry and concrete rising 130 feet above the riverbed, more than 100 feet thick at its base. A conventional bomb dropped from altitude would hit the crest, if it hit at all. And that was the thing Bomber Command's own research had painfully established. The average bomb in the early war years didn't fall within yards of the aiming point. It fell within miles of it. Even by 1943, circular error probable was measured in hundreds of yards. The dam crest was a ribbon roughly 25 feet wide. The mathematics were merciless. And even if some miracle placed a bomb on that ribbon, an explosion on the surface would waste its energy pushing against air that simply yielded and dispersed. Useless. The Germans knew what they had. They'd strung heavy torpedo nets across the reservoir on the waterside to catch any mine or torpedo. Light flak positions bristled on the dam towers and surrounding hills. By every conventional measure, the Möhne was indestructible. The problem was closed, filed away. Except Wallis didn't accept the word impossible. He never had. Born on September 26, 1887 in Ripley, Derbyshire, Wallis had trained as a marine engineer before joining Vickers Aviation Works at Brooklands in 1913. His career had been brilliant in ways that only engineers truly appreciated. In the 1920s, he'd served as chief designer on the R-100 airship, a privately built craft that was safer and better engineered than the government's rival R-101, which crashed in 1930, killing 48 people and destroying British confidence in airship travel forever. Wallis's superior design was scrapped along with the entire programme. A bruising lesson in how institutional politics could crush good engineering. He never forgot it. By the late 1930s, working at Vickers Armstrong's in Weybridge, he'd invented the geodetic airframe, an interlocking lattice structure used in the Vickers Wellington bomber that distributed loads so ingeniously that Wellingtons routinely flew home with enormous holes torn in their fuselages by flak, damage that would have been fatal in any conventionally built aircraft.
The geodetic lattice wasn't a weapon, it was a way of thinking, a refusal to accept that structural problems had to be solved the way everyone else solved them. So when Wallis looked at the dam problem, he didn't see a military impossibility, he saw a physics puzzle with a missing variable. And the missing variable was water itself. Here's what most military planners had overlooked. You didn't need to hit a dam from above. You needed to detonate a massive charge directly against the upstream face of the dam, deep underwater, where the incompressible nature of water would do the real work. An explosion in open air wastes most of its energy. An explosion underwater, hard against a solid wall, has nowhere to go. The water can't compress, so it transmits the shockwave with devastating efficiency straight into the structure. A contact charge at 30 feet of depth could exert forces on the dam wall equivalent to many times what the same explosive would achieve in air. The physics was crystal clear. The delivery mechanism was the impossibility. Torpedo nets blocked the water. Anti-aircraft guns guarded the sky. How do you place 9,000 pounds of explosive against a dam wall 30 feet underwater when every obvious route is sealed? By the end of March 1941, Wallis had completed a paper titled A Note on a Method of Attacking the Axis Powers, laying out the strategic case for destroying Germany's energy infrastructure rather than area bombing cities. It circulated among a few sympathetic officials. It was largely shelved. Wallis kept working, and those marbles in the garden tub gave him his answer. A marble thrown with sufficient speed at a shallow angle didn't sink. It skipped. It bounced forward across the water surface in diminishing hops, exactly like a stone skimmed across a pond. And a bomb that could skip across a reservoir would leapfrog cleanly over torpedo nets and deliver itself to the dam wall like a self-guided torpedo that needed no guidance at all. By April 1942, the garden experiments had crystallized into a formal paper. Spherical bomb, surface torpedo, describing a weapon that would combine the properties of both. But here's the thing about Barnes Wallis. Colleagues described him as courteous, soft-spoken, a man of deep Christian faith who'd tried and failed to enlist in the army during the First World War because of his eyesight. He wasn't a weapons designer. He wasn't a military man. He was an aircraft structural engineer with a washtub full of marbles, and an idea so audacious that when it reached the desk of Air Chief Marshal Sir Arthur Bomber Harris, the Commander-in-Chief of Bomber Command, Harris's response was immediate and withering. This is tripe of the wildest description. There is not the smallest chance of it working. Harris wasn't a fool. He understood better than most the chasm between an elegant diagram and a weapon that works at night under fire. The concept sounded preposterous. It required diverting scarce Lancaster bombers from the main bombing offensive. It demanded a new squadron of experienced crews pulled from existing units. And it was being proposed by a civilian who designed aircraft frames, not ordnance. From Harris's perspective, the bouncing bomb was a vanity project, dreamed up by a boffin who'd never heard flak burst against a fuselage. So Wallis, quiet, non-political, fundamentally uncomfortable with confrontation, was forced to become something he'd never been. A lobbyist, a salesman, a bureaucratic guerrilla fighter. He arranged screenings of test footage for senior officials, showing film of scale models bouncing across water tanks at the National Physical Laboratory in Teddington. He worked contacts within the Ministry of Aircraft Production. He fought on two fronts simultaneously, the physics in the laboratory and the politics in Whitehall. And now we get to the part that makes this story something more than military history. The physics. The central insight, the thing that elevates the upkeep bouncing bomb into one of the most extraordinary weapons ever conceived, was backspin. Wallis understood that a smooth object dropped onto water at speed would bounce, but erratically, veering, tumbling, sinking short. A skipping stone works because a skilled thrower imparts spin, which gyroscopically stabilizes the stone's attitude and keeps it striking the water at a consistent angle on each hop. Wallis needed that stabilization. But he needed something more. He needed the bomb, once it had bounced its way to the dam face and its forward momentum was spent, to not simply bob against the wall and float there uselessly on the surface. He needed it to crawl down the wall. And the solution to both problems, stabilization during the skip and downward crawl at the wall, was the same elegant trick. By spinning the bomb backwards, opposite to its direction of travel, at 500 revolutions per minute before release, Wallis achieved two things at once. The backspin gyroscopically stabilized the bomb through each successive bounce, keeping it on a true course across the reservoir. And when the bomb finally reached the dam, with residual backspin still turning, that spin gripped the concrete face and pulled the weapon downward like a wheel rolling down a vertical surface. It didn't float away. It hugged the dam wall and sank, positioning itself exactly where the physics demanded. Think about that for a second. One variable, backspin, solving two completely different problems simultaneously. That's not engineering, that's artistry. The mechanical system was improvised brilliance. A Vickers hydraulic motor mounted inside a modified Lancaster's bomb bay, connected to the cylindrical upkeep weapon by a belt drive. Before release, the motor spun the bomb up to 500 revolutions per minute while it hung in calipers beneath the aircraft's belly, rotating like an enormous top. The aircrew could hear the vibration thrumming through the airframe, feel it in their bones. The bomb couldn't be carried internally. It was too large, and it had to spin. So it hung exposed beneath the fuselage, bomb bay doors removed entirely, adding drag and making every modified Lancaster unmistakable to anyone who saw it. The release parameters were merciless, exactly 60 feet above the water, exactly 232 miles per hour, rounded to 240 in operational briefings. These weren't guidelines, they were hard constraints imposed by physics. Too high, the bomb would strike at too steep an angle and either shatter or plunge through the surface. Too low, and the aircraft risked hitting the water or being destroyed by its own weapon's blast. Too fast, and the impact energy would exceed the structural tolerance of the casing. Too slow, and it wouldn't achieve enough bounces to reach the dam. Release point, 400 to 450 yards out, roughly 5 to 7 skips across the surface. And once the bomb had walked itself down the dam face, 3 separate hydrostatic pistols, pressure-sensitive fuses, registered the increasing water pressure as the weapon sank. At a preset depth of 30 feet, they fired. The main charge, 6,600 pounds of Torpex, a compound 50% more powerful than TNT by weight, packed inside a weapon weighing 9,250 pounds total. Every variable interlocked with every other. Change one, and the whole mechanism failed. Getting them all right nearly destroyed Barnes-Wallis before the weapon ever reached Germany. After scale model tests at Teddington and explosive trials against a disused dam at Nanty Grow in Wales, which proved an underwater contact charge could indeed breach a dam wall, full-scale drops began at Chesil Beach in Dorset, then moved to Reculver on the Kent coast. These trials, in the desperate early months of 1943, were a cascade of failure. The original design used a spherical wooden outer casing enclosing the cylindrical Torpex charge. Prototype after prototype was dropped from modified Lancasters. Prototype after prototype disintegrated on impact. Wooden casings cracked, shattered, splintered into wreckage. Weapons that survived impact veered off course or sank after one or two bounces. Wallis stood on the Kent shoreline with his colleague A.D. Grant, timing the bounces with a stopwatch, and watched months of theoretical work reduced to splinters and spray. The timeline was suffocating. The entire operational concept depended on attacking in May, when reservoirs were at maximum capacity after the spring snowmelt. Full reservoirs meant maximum flooding when breached and maximum hydrostatic pressure on the dam walls. If Wallis couldn't deliver a working weapon by mid-May, the window closed, water levels dropped, and the project, already dismissed by Bomber Harris as tripe, would be cancelled forever. He had weeks, not months. And the bombs kept shattering. Accounts from colleagues and biographers describe a man approaching emotional collapse during the Reculver trials of April 1943. He'd invested not merely his professional reputation, but his entire moral conviction. He believed this weapon could shorten the war, and every broken casing on the Kent shoreline was a verdict on his judgment. He was 55 years old, exhausted, fighting a war on two fronts and losing both. And that's when he made the decision that saved everything. He abandoned the spherical casing entirely, stripped it away, dropped the weapon as a bare cylinder, just the Torpex charge in its steel skin, spinning naked beneath the Lancaster. It looked crude. It looked like surrender. But when the cylindrical upkeep was dropped at Reculver, it bounced. Cleanly, consistently, surviving impacts that had shattered every sphere. The final successful trials took place days before the raid had to launch. Days. The margin between triumph and cancellation was measured in hours. On 21st March 1943, 617 Squadron was officially formed at RAF Scampton in Lincolnshire under Wing Commander Guy Gibson, a 24-year-old veteran of over 170 operational sorties. Gibson was everything Wallis was not. Young, instinctive, charismatic, a natural combat leader with a hunger for action that bordered on recklessness. His crews were hand-picked from across Bomber Command. Experienced men told almost nothing about their mission except that it would require extremely low-altitude flying over water. In darkness. Even Gibson wasn't initially briefed on the target. The secrecy was absolute. They trained for barely 8 weeks. Derwent Reservoir in Derbyshire. Ibrook near Effingham. Thundering across the English countryside at treetop height while navigators confronted the problem that would determine whether this mission was survivable or suicidal. At 60 feet above a flat, featureless body of water in darkness, a standard barometric altimeter was useless. A few feet of error meant the difference between a clean bomb release and a Lancaster cartwheeling across the surface at 230 miles per hour. The solution was so simple it's almost heartbreaking. 2 Aldi's lamps mounted beneath each Lancaster. One under the nose, angled rearward, one under the tail, angled forward. Calibrated so that at exactly 60 feet, and only at exactly 60 feet, the 2 spots of light converged into a single figure-of-8 pattern on the water's surface. Too high, and the spots drifted apart. Too low, and they merged into a blob. The navigator peered down through the fuselage and called corrections. Down a bit. Up a bit. Steady. 2 lamps. A geometry problem. life or death, reduced to whether two circles of light were touching. It was the marble in the washtub, scaled up to a 30-ton bomber. The bomb-aiming challenge was solved with equal elegance. A handheld triangular plywood sight with two pegs set at precise spacing. The bomb-aimer looked through it and lined the pegs up with the towers at either end of the dam. When they aligned, the aircraft was at the right distance. A device you could build in a shed. It worked perfectly. On the evening of 16th of May 1943, the crews of 617 Squadron were finally told what they were about to do. Barnes Wallis was there at Scampton in the briefing room. 19 modified Lancasters would fly in 3 waves. The first wave of 9 aircraft, led by Gibson, would hit the Möhne and then the Eder. They flew low across the North Sea and occupied Europe, so low that radar couldn't find them, in places barely above the wave tops, threading through gaps in the flak belts at extreme low level. At the Möhne, flak opened up immediately. The first bombs had to be placed with absolute precision. 60 feet, 232 miles per hour, the right distance, while tracer fire ripped across the water. Gibson attacked first. His bomb bounced cleanly, struck the dam, crawled down and detonated, a colossal pillar of white water erupting into the night. But the dam held. The second aircraft, flown by Flight Lieutenant John Hopgood, was hit by flak on the approach. His Lancaster was burning as it crossed the dam. The bomb, released late, overshot the wall and detonated beyond it. Hopgood's aircraft crashed in flames. He and most of his crew were killed. What Gibson did next was not in any tactical manual. On every subsequent attack run, he flew his own Lancaster alongside the incoming bomber, parallel to the dam wall, deliberately drawing fire from the flak positions to give the bomb-aimer a few undisturbed seconds. Flight Lieutenant Mickey Martin's bomb overshot slightly. Squadron leader Dingy Young's upkeep struck true. Then Flight Lieutenant David Maltby made his run, and the Möhne broke. A wall of water surged through the breach into the valley below. Gibson took his remaining aircraft to the Eder, which was undefended by flak, but presented a nightmare approach. A narrow valley with a steep descent that forced pilots into a gut-wrenching dive before levelling at 60 feet over the reservoir with almost no margin. It was Pilot Officer Les Knight who finally placed his bomb perfectly against the Eder's face. The dam breached. The Sorpe, an earthen embankment dam with a concrete core, a structure that absorbed shockwaves rather than transmitting them, requiring a completely different attack profile, along the dam's length rather than perpendicular, took only one direct hit and survived. But here's what happened to the men who turned Wallis's physics into reality. 8 of the 19 Lancasters didn't come home. 53 aircrew were killed that night. 3 more were taken prisoner. Many of the dead were in their early 20s. They were shot down by flak, crashed into power lines they couldn't see at 60 feet in the dark, killed when their Lancasters struck trees or obstacles in the darkness, flying so low that the margin between life and death was measured in single feet. Out of 133 men who took off from Scampton, 53 never came back. Barnes Wallis, who had stayed up through the night at Scampton waiting for news, learned the toll as the surviving aircraft trickled home through the dawn. By accounts from those present, he was devastated, shattered in a way that the Reculver failures had never managed. He reportedly said that if he'd known the cost, he wouldn't have started the project at all.
The man who'd solved the impossible problem was broken by what it cost.
Water from the Möhne breach alone surged through the Ruhr Valley, flooding towns, destroying infrastructure, killing an estimated 1,600 people on the ground, among them many hundreds of forced labourers, including Soviet and Ukrainian women held in camps near the Möhne, who had no warning and no means of escape. A horrifying footnote that Wallis could not have anticipated and could never have wished for. Wallis went on. He always went on. He developed the 12,000-pound Tall Boy, an earthquake bomb that could destroy targets conventional ordnance couldn't touch, and the 22,000-pound Grand Slam, the largest conventional bomb of the war, which crushed railway viaducts and submarine pens. He was knighted. He worked into old age on swing-wing aircraft designs, still pushing at the edges of what engineers said was possible. But he never fully escaped the weight of those 53 names. The mathematics of backspin and hydrostatic pressure had been proven devastatingly correct, and 53 young men had paid for the proof. Think about him in that garden in Effingham, a quiet, soft-spoken, deeply religious aircraft engineer, flicking marbles across a washtub, counting bounces, taking notes. Somewhere in the behaviour of a glass marble hitting water at speed, he could see a solution that the entire British military establishment had declared impossible. And he was right. The physics was right. Every variable, 500 revolutions per minute, 60 feet, 232 miles per hour, 30 feet of depth, 6,600 pounds of torpex, interlocked into a mechanism of extraordinary precision and elegance. He refused to accept impossible. He proved that impossible was just a physics problem nobody had bothered to solve yet. And he carried the weight of what that proof cost for the rest of his life. Subscribe for more stories like this.